Welcome, ladies and gentlemen, to another exciting episode of Dave Does Math from Home. On today's episode, we're talking about section 5.2, which is called the definite integral. Probably this word is new for you, so I want to take some time to explain what this is talking about, where it comes from, how it's related to the last section, and where we're going with it. So definite integral is a fancy way of saying the exact area beneath a curve. So in the last section, 5.1, we were doing approximate areas. We were using Riemann sums with a different number of rectangles to approximate the area below a curve. But those approximations always had some margin of error in them. Because we were using rectangles to approximate a curved area, like there was always going to be some extra piece missing or some extra piece that wasn't completed. So we always had these approximations. And we saw in the last video for 5.1 that you could make your approximations more and more and more, increasingly more accurate by using more rectangles. So the general idea here is, what if you use infinitely many rectangles? If you get more and more accuracy for each rectangle, then using infinitely many should give you perfect accuracy. The question then becomes, how do we reasonably use infinitely many rectangles? And don't panic, we're not going to. We're going to talk about the idea of it and how it's definitely rooted in this idea of Riemann sums, but I'm not currently going to make you do any limits of Riemann sums with infinitely many rectangles. That's not a good use of our time right now. I do want to talk about the notation of it though. So when we did Riemann sums, the fancy way of writing a Riemann sum looks like this. The sum from I equals 0 to n f of x sub I times delta x. And we've seen some of these symbols before. Like x sub I was the fancy book notation for all of the different endpoints across the interval. So when we had an interval from 0 to 6 with in 6 subsections, our x sub i's were 0, 1, 2, 3, 4, 5, 6. When we did that in 3 sections, these x sub i's were 0, 2, 4, and 6. So these are just like your indexed x values. This symbol is the Greek letter sigma, and it means sum. And we saw from the last section that delta x was the width. So essentially, these are heights, which were the function values. This is the width, which is just a distance on the x-axis. And this means the sum over all of these I values. So you do it when x is 0, and you do it when x is 1, and you do it when x is 2, and 3, and 4. So this is the super fancy way of writing our Riemann sum. I guess the left sum would go from 0 to n minus 1, and the right sum would go from 1 to n. But approximately, this was how we did our Riemann sums. Here's what we're going to do with this now. The idea is we can get perfect accuracy by taking infinitely many rectangles. So we're going to take this idea of a Riemann sum, and we're going to take the limit as n goes to infinity of this thing. And when you take that limit, you get something that's relatively similar, but it looks different. Instead of the Greek letter sigma for sum, we're going to use a big scripty S. Instead of this being indices, so like the number of rectangles, right now the way this is written from I equals 1 to n, this is counting up one by one for each rectangle. So this is an increasing index in a list. On this, we're going to use A and B to represent the interval from A to B. So if we were doing this on the last problem, this would be our 0 and our 6. These are the bounds of your integral. F of x isn't going to change much. We're not going to use x of i's to represent a collection of different x values. We're just going to call it f of x, as x varies between these two bounds. And I think the most important change, when we take the limit as x goes to infinity, this width shrinks. It's really, 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 really small. Some would say it gets infinitesimally small. And so instead of writing that as a delta x, which is a measurable, substantial difference between two x values, we're going to call this the infinitesimal distance between two x values. And believe it or not, we've seen something like that before. It's dx. In the same way that a slope started as delta y over delta x, and eventually with calculus we started thinking of this as dy over dx, because this slope was about distinct discrete points, two distinct discrete points, and when we shrunk that discrete distance down to nothing, these deltas turned into d's, and now this is just the instantaneous slope, instantaneous rate of change, instead of between 2 points. The same thing is going to happen with our delta x here. Here our delta x shrunk infinitesimally and became a dx when the distance between 2 points got to nothing. So the same thing happens here. Our delta x is going to shrink to almost nothing and become a dx. This still means sum. This is still a height. This is still a width. But now this thing all together means definite integral, which means the exact area beneath the curve. So that's sort of the conceptual theory behind what we're doing here. Or I should say, that's the conceptual theory behind the notation of what we are doing here. We are not actually going to take Riemann sums with infinitely many rectangles. That would be absurd. No one has time for that. I just want to introduce you to the idea of using infinitely many rectangles to increase the accuracy, and how these symbols with a sum over an index of heights times widths turns into this sum over an interval of heights times widths. That's all this is about. I'm just introducing you to notation and where it comes from. So, if I'm not actually going to force you to do Riemann sums with infinitely many rectangles, how am I going to get you to get exact areas in this section? And the answer is, we're going to do a small subsection of problems that can use geometry. So let me tell you what I mean by that. Let's say we have a function f of x equals 2x minus, no, we'll do 2x plus 3. I don't even want to do that. Let me just do x plus 2. This will be nice. F of x equals x plus 2. I want the definite integral of f of x dx from, let's say, 1 to 5. If I draw this function, f of x equals x plus 2, it looks like a straight line. Has a slope of 1, goes through 2. So here's x equals 1, here's x equals 5. I can find the values of these points. This is y equals 3. This should be y equals 7. So I'm asking for this area. Astute observers will note that this is a trapezoid. In the last video, we had to do Riemann sums because we had weird curvy business between these 2 points. If we have a straight line between these 2 points, we know the area formula for this. We know the area of the trapezoid. Or if you don't like trapezoids, call it a rectangle and a square. We know the area of this rectangle. We know the area, I'm sorry, not a rectangle, a square, rectangle and a triangle. We know the area of a rectangle. We can find the area of a triangle. Shouldn't be too bad. This width is 4. This height is 3. This height here should be from 3 to 7 is 4. And this width is still 4. So this area should be, this rectangle has area 12. And this triangle has area 1/2, 4 times 4 is 8. 20. The area beneath f of x between 1 and 5 is 20. That's all we're doing. There's actually a lot of functions that you can use geometry to figure out. Functions that have straight lines. When you take an area between 2 x values, it'll pretty much always turn into a trapezoid. The other fun thing we can do this to is circles. So let me do circles, and then we'll talk about some other weird things to be aware of in this section. Let's say f of x equals the square root of 16 minus x squared. This is a semicircle of radius 4. Hopefully you can just sort of recognize this. If y equals 16 minus x squared, you could square both sides and then move the x over and get y squared plus x squared equals 16. That's what makes this, or I'll call it 4 squared. That's what makes this a circle of radius 4, because it's the positive square root, not the negative. We have the top half of the circle, so we get the semicircle. So, the definite integral from -4 to 4 of f of x dx is 1/2 the area of a circle. So 1/2 pi r squared, which would give me 1/2 pi times 16, so 8 pi. This is still pretty much what we're doing in this section. We're taking functions that create shapes that we know the area formula to, and we are getting areas out of those things. There are a couple more slight weirdnesses to this section that I need to talk about, so I'm going to start a new video to talk about those. But this one's already at about 13 minutes, so I'm going to cut this one here. We'll put the other stuff in a part 2. Stay tuned.